Welcome everyone. In this video we will solve a very interesting physics Olympiad question from a Turkish physics Olympiad. Here is the question. And also I will attach the original paper to the descriptions part so that you can have a look at the question yourself. We have a capital mass, capital M. There will be a little m in contact with it, and there is a pulley which connects this little m to the wall in such a manner. The gravity, of course, is downward, so the gravitational field strength is downward. And we are told by the question that there is friction between capital M and the surface and between the two masses. The coefficient of kinetic friction for each contact is F. And this F is given by the question to be 1/3. Also, in the question we're told that little m is greater than capital M. I really could not figure out why they told this, and it doesn't really look nice, I need to admit, because it isn't conventional to do so. And really, I carried out the calculations myself, and I didn't encounter a point where this is helpful. So maybe you might try to make sense of this and tell me, hey, this is why they told this, okay? I really would be interested to hear the reason behind this if you can find it. But yeah, this is it is there, but I can erase it. I really did not use it in my calculations. So, we are asked to find the acceleration of capital M, which I will call A. What is A? How do we start? Well, I think to start, we can just choose a direction of motion for this. Let's say that mg, this guy, is going downward with an acceleration of a, which would mean that this portion of the rope is getting longer. Hence, this portion should get shorter. So, from that, I can conclude the acceleration should be to the right. But also, I know one other thing. I know that the length of the rope should be conserved. So, how much it decreases in one side, it should be compensated by the increment in the other side. Which means that this acceleration is also A. Alright, I also want to mention one important thing. This acceleration is not the whole acceleration of little m. It is also accelerating to the right with the same acceleration as capital M. The only reason I didn't show it is because to not confuse the picture, okay? Maybe let's show it though. So what we can say is little m is accelerating downward and to the right relative to the ground, but it is only accelerating downward relative to the capital mass. Alright? Now we will start off by drawing the force diagrams, the forces that act on each object. Let's start with the small m. There will be mg downward, there will be tension upward. There will be a normal force by the capital mass to the right, it will be a push. And since there is friction, there will be a frictional force. And which direction will it be? It will be in the opposite direction of motion. And since we release this system from rest, the direction of motion is the same with the direction of the acceleration. So it is downward, which means the force of friction is upward. And it is going to be coefficient of kinetic friction times the normal force. Cool. Now let's draw the free body diagram for the capital M. So capital M, there will be the gravitational force again, downward mg. There will be a normal force by the ground. This is not N1, notice, this is just N. Then there will be a push N1 by the little m. Also, there will be a downward frictional force, Fn1. How do I know that it is downward? Well, Newton's third law tells me that every action requires a reaction, opposite in direction, equal in magnitude. But there are other forces as well. For example, there will be a force to the left. This is another friction, but it is this time F times N, because this is the frictional force by the surface, not by the other mass. And are we done? You might say yes, but there are two other forces left, which are, I believe, the easiest ones to forget for this question. There is a tension to the right exerted by this rope. There's a tension, and there is a tension downward exerted by this rope. And you might be saying, hold on a second, how can that be the case? Capital M is not connected to any of the ropes. That is correct, but it is connected to the pulley, and the pulley will be sort of transferring that tension in the rope, okay? And also you can notice that this tension should exist, because otherwise the force diagram would be the same. For this case, we have a tension, and, well, A is not like that. Mass is like this, little m. It is falling downward without any tension, and the force diagram would be the same for this guy if we don't include the tension. But since the tension is there, we need to include it, because, as I said, if we were to cut the rope, the force equations would not change if we are not writing this T here. So that is one way that you can convince yourself that there is in fact a tension, or you can simply say that there is a pulley, it transfers the tension, okay? Now I want to choose the coordinate system for both, like so. Notice that I took the direction of the accelerations to be positive. And we now start with the little mass. Little mass has so in the x direction. For the x, we can see that N1 provides all the acceleration, which we said is ma. For the vertical, we will have mg minus t minus fn1 equaling ma. Notice that these are the same a. And since we know that N1 is equal to ma, we can substitute it here to get that mg minus t is equal to, so it is going to be fma plus ma, but since f is 1 over 3, it will simply be 4 over 3 ma. Cool? And this is in fact all that we can get from the little m. So let's move on with the capital mass. This was little mass, this is capital mass. For the x direction in the capital mass, we will have t minus n1 minus fn equaling ma. And for the y direction, we will have, there won't be an acceleration in the y for capital mass, so the upward forces should balance the downward forces. The only upward force is n. It will be balanced by, let's see, mg plus t, what else, plus fn1. Cool. Now, at this point, it might be hard to see the next step ahead, but if you look careful enough, you can say, we don't want the tension to appear in the final result, so let's just substitute for it. And we find the substitution expression by solving this equation for t, so it is going to be that t is equal to mg minus 4 over 3 ma, which I then substitute in x and y equations. So that what do we have? We have mg minus 4 over 3 ma minus n1. What is n1? It is ma. So minus MA. And let's just combine the two terms. Minus 4 over 3 minus 1, it is minus 7 over 3 MA. Minus 7 over 3 MA. Minus Fn, which is just going to be, since F is 1 over 3, it is going to be 1 over 3n, equaling MA. Now let's focus on the y equation, because why not? And that tells us that n is equal to mg. For t, I substitute mg minus 4 over 3 ma. And then we have f times n1. So it is 1 over 3 times n1 is ma. And let's just add the last two terms to get minus ma. Now at this point, I think you can realize that if I multiply the top equation by 3, so I have 3, this coefficient is cancelled, this coefficient is cancelled, this is 3. And if I add them side by side, I get rid of this n. And I will be able to solve for a in terms of the given quantities. So let's just do that. We will have 3mg minus 7ma equaling 3ma minus ma plus mg plus mg. So where does that lead us? Let's subtract 1 mg from the one side, so 2 mg. So alright, so we handled these two guys. Let's put this guy to the other side. Minus mg equals, let's toss this guy to the other side. So plus 7 minus 1 plus 6 ma. And then finally we handle this guy. It stays as it is, plus 3 ma. Which means that a is going to be equal to 2m minus m divided by 6m plus 3m g. Anyways, this is it for this video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.